So in this video, we're going to evaluate limits analytically, which means using algebra, and the limits that we're going to be checking out will end up having infinity or negative infinity as the result. Now, as we go through the examples that you see on screen here, make sure you're paying attention to some of the indicators that are going to tell us, hey, this is why this answer is going to be infinity or negative infinity. Now, before we do any of these four examples, you need to be pretty well aware of what we're going to talk about over the next two screens. So if I let x get closer and closer and closer to 0, and I think you would agree with me that in this column we have x getting closer and closer to 0, what happens with 1 over x? Well, 1 over 100, I can change that into multiplication by the reciprocal, and 1 over x is going to have a value of 100 if x is 1/100th. How about 1/100,000th? Well, if I use the same strategy, change it to multiplication by the reciprocal, I get 100,000. Now, I realized as I was looking at this, I have 100 million down here, and I only wrote 1 million here. I just left off a couple of extra zeros in this spot. This should be 100 million. The point to make here is as x approaches 0, 1 over x is approaching positive infinity, unless x is approaching 0 from the smaller side. If x is approaching 0 with negative fractions, all of that work that we did on the prior screen, and I copy and pasted it, so I'm still missing some zeros here, all of that work from the prior screen still applies. All the signs have changed. So as x approaches 0, 1 over x is either approaching negative infinity, as you see on this screen, or positive infinity, as you saw in this one. So here's the thing that you're going to have to do when you're evaluating limits, and something like this that you see in the upper right corner happens when you attempt to plug x in. X is approaching 0. I put 0 in place of this x. I square it, stays as 0. 1 divided by 0, hey, that's an undefined answer. There's a difference between, for the purpose of evaluating limits, being undefined and being indeterminate. Indeterminate often means you're able to get a finite value for your limit. That would be 0 over 0. That's not our situation right now. Our situation is non-zero divided by 0. Based on those tables on the prior screen, non-zero divided by 0 should have an answer of plus or minus infinity. The way that we're going to figure out which it is we're going to carefully consider one-sidedness. So if I break this up into the limit as x approaches 0 from the bigger side and the limit as x approaches 0 from the smaller side, I'm going to be plugging a number slightly bigger than 0 in for x and just reasoning out what happens. When I take that number slightly bigger than 0, put it in place of the x that's in the bottom, I'm going to square it. Squaring 0 keeps it a 0. Squaring a positive keeps it a positive. Positive divided by a positive, positive infinity for this answer. Reason why I don't have equal signs working across this line, you never technically get to infinity, so you never equal infinity. So you have to kind of pay attention to your teacher or your professor as far as whether or not they allow you to say that something is equal to infinity. They might want you to say, and that's kind of the notation I've used, approaching infinity rather than equaling infinity. Other side of 0, same strategy. I put the value that x is approaching, 0 from the smaller side, in for x, and then I just have to reason out what's happening. 0 squared is still 0, but a negative squared turns into a positive, and a positive divided by a positive is positive infinity. Because these one-sided limits both approach positive infinity, the general limit also approaches positive infinity. So as we see this occur early in our limit, non-zero divided by 0, that signals check one-sided limits to see if you get positive infinity or negative infinity, and carefully considering that one-sidedness should allow you to reason out what the sign of the result is going to be. In this case, they both ended up being the same sign, which is why we give the conclusion of positive infinity for the initial limit. This one's got a little bit more going on, but we're still going to go with the same initial step. Plugging -2 in place of all of the x's is going to give me -1 in my numerator. And if you look at the denominator, it's already in a factored form. -2 going here, adding 2 gives me 0. No matter what this ends up being, my denominator is 0. So in this case, I end up with non-zero divided by 0. That signals an infinite answer. We don't know if it's positive infinity or negative infinity unless we consider one-sidedness. So we're breaking this up into two one-sided limits once again. So as I do that, a little bit different notation here, and I do want to take a minute to try to get you on board with what I'm doing. I'm trying to carefully consider one-sidedness. In this last limit, there was only a single x, so it wasn't really as involved as what we're seeing in this one. In this new limit, there are 1, 2, 3 x's that I've got to put this number slightly bigger than -2 in place of. Now here's why I don't have a one-sided indicator on this -1 or this -5. I know if I put -2 in place of this x and add 1, I get -1 in the numerator. Is that technically slightly above -1 or below -1? I don't care. It's either -0.9 or -1.1. All I need to know about the numerator is that it's negative. Similarly, when I put -2 in place of this x, I get really close to -5. Is it -4.9? Is it -5.1? Again, I don't care. I know it's negative. So the only thing that you have to be really, really cautious with when you're doing this sort of analysis is that one spot in the denominator where the 0 gets generated. And that's in this second factor. And I would definitely suggest if your limit that you're doing, the function within the limit that you're doing is not in a factored form. If it has a factored form, I think this reasoning is a little bit easier to do with a factored form. So you might need to get your denominator to look like this if it doesn't look like that from the onset. But in this case, I know that this is negative, I know that this is negative, and when I put the number slightly bigger than -2 here and add 2, I get slightly above 0. Now with this fraction, I'm just going to follow the order of operations. So I'm going to do the multiplication in the bottom. 5 times 0 is 0, but a negative times a positive is a negative. Something divided by 0 is infinite, but a negative divided by a negative is a positive. On the other side of -2, same strategy. And again, I don't care whether this is -1.1 or -0.9. I don't care whether this is -5.1 or -4.9. I need to know that those positions generate negatives when I put -2 in for x. This is the place where we've got to be really detailed. Something slightly smaller than -2 goes here, something like -2.1. I add 2 to it. That doesn't quite get me clear back up to 0. From -2.1, adding 2 is going to leave me slightly negative. Follow the order of operations with this fraction. 5 times 0 is 0, but a negative times a negative is a positive, and then a negative divided by a positive is a negative. The original limit does not exist. The original limit does not exist not because of that initial indicator. So one of the mistakes I'll see students make quite a bit, they'll say, all right, well, hey, I get something undefined, my limit doesn't exist. It does, but the reason why it doesn't exist is because we've shown we're approaching one value from the bigger side of -2 and a different value from the smaller side of -2. So this one here is a little bit more involved. We're approaching pi by 2, and we're considering the tangent function. Same initial step, put pi by 2 in place of x. Now, if you're not using the calculator, which I'm sure in most of your calculus courses you are not, you're going to be probably using the unit circle to reason through this one. So I've got a few different versions of the unit circle that we'll go work through on the way through this example. Tangent is sine of x divided by cosine of x. So I'm needing to do sine of pi by 2 divided by cosine of pi by 2. So pi by 2 is equivalent to a 90-degree angle. I know that sine corresponds to the y-coordinate, which is +1. I know that cosine corresponds to the x-coordinate. The x-coordinate here is 0. 1 divided by 0 is undefined. It is undefined because it's an infinite answer. Now, is it positive infinity? Is it negative infinity? We don't know unless we consider one-sidedness. So I'm considering the smaller side of pi by 2, and then I'm also considering the bigger side of pi by 2. So if I consider the smaller side of pi by 2, this tangent fraction, which I'm still maintaining use of sine divided by cosine, so that we can still use the unit circle for this reasoning, is going to be involving an angle slightly beneath pi by 2. So if you'll notice what I did on this unit circle in the middle, I haven't quite opened up from 0 clear to pi by 2. I've stopped a little bit shy. So if I'm using degrees, I'm at an angle that's slightly beneath 90 degrees, 89 degrees, something like that, right? Slightly smaller than pi by 2 radians. I don't, again, care whether this is slightly below -1 or slightly above -1. I need to recognize that this position is positive. Now for my denominator, what happens with cosine of this sort of angle that I've plotted? Keep in mind, cosine is the x-coordinate of a point that you plot on the unit circle. The x-coordinate is slightly positive. So I have 1 divided by a small positive, and that is going to give me a big positive answer. Positive divided by a positive gives me that big positive answer. Going to the opposite side of pi by 2, the bigger side of pi by 2, so you'll notice I'm opening to an angle slightly beyond pi by 2 from the positive x-axis, so slightly past 90 degrees. Again, my numerator, I don't care if it's 0.9 or 1.1, it's positive. My denominator, my x-coordinate from this location on the unit circle, is now slightly negative. Positive divided by negative, negative answer. This is a really negative answer. Once again, one-sided limits do not equal. That's what tells us the general limit does not exist. It's not because of what we saw back here. This happening when you're evaluating limits indicates an infinite answer. The only way for you to figure out if it's positive or negative is to consider one-sidedness, and if you see one positive and one negative, which has happened in each of the last 2 examples, that's when you give that conclusion of does not exist. Last example in this video, probably the trickiest because of the nature of the function that we're dealing with. We're supposed to approach 2 for this function that you see here. Now what catches my eye about this, I do get division by 0 whenever I put 2 in place of the x's, but I also end up with a square root of 0 in the denominator, and that's an issue if you're on the smaller side of 0. So if you're dealing with square roots, you do have to make sure you're in the domain of the function. So the domain of this function, I guess I didn't indicate it correctly. I'm just really considering what can go into the root. What can go into the root here is going to be anything that is between -2 and 2, right? I want what's under the root to be greater than or equal to 0. So what can go into the root is between -2 and 2, including both endpoints. Technically, I can't put -2 or 2 into the whole function. So my use of the term domain here is technically not correct. This is what can go into the root. Well, now that we see that we can only approach 2 from the smaller side, the bigger side of 2 is going to be a limit that does not exist. That's a limit that's one-sided that does not exist because we can't approach 2 from the bigger side. We end up trying to take the square root of a negative. Why am I checking the one-sided limits? Because I get the indicator that we've seen throughout every example so far, non-zero divided by 0. Is my answer infinity? Is my answer negative infinity? I consider one-sidedness. What makes this problem really weird is this issue here. I can't put a number bigger than 2 in place of this x. Therefore, my general limit is also going to not exist when one of the one-sided limits doesn't exist. So you can get this conclusion that you see at the bottom here just based on recognizing I'm going to get the square root of a negative when I put in a value slightly above 2. Now let's say you were just asked to check the limit on the smaller side of 2. What would that be? We don't need to do this work in the middle here to get the conclusion about the general limit. We already know that's the case based on not being able to approach from the bigger side of 2. But if you were given a one-sided limit, which you are asked to evaluate from time to time in practice problems, test and quiz problems, what would you do? Well, you would get the indicator, -2 divided by 0. So carefully considering one-sidedness, when I take that number slightly smaller than 2 and I square it, I get an answer slightly smaller than 4. 4 minus a number like 3.9 gives me a small positive. The square root of a small positive is going to still be a small positive. A negative divided by a positive is negative infinity.